I'm actually going to break this lecture up into two parts. So in part one, I'm going to talk about the basics of signal processing. So I'll cover things like match filtering, how we construct CBC waveform models, and how we treat the data. Some of this was already covered yesterday, but it's always good to go over things again. In the second part, I'm basically going to cover the detections that we have from the first two science run and what we can do in terms of the actual science applications. So first of all, signal processing and match filtering. So the thing about gravitational waves is that they're analogous to 1D sound waves. We're never going to have any pretty pictures of gravitational waves, but you can basically boost up the frequency and stick them on an MP3 player and listen to them. So if you have a signal that's buried in Gaussian noise, the optimal method for detecting that signal is called match filtering. And it works by correlating a known template or a known waveform model against the data. So how do we construct the optimal filter? So let's begin with some type of data output, which is a combination of a signal and some noise, where we're going to assume that the amplitude of the noise is much, much greater than the signal. We can define a correlation between the signal or the output and some real filter in the time domain and correspondingly in the Fourier domain. So what we actually want to calculate is the signal to noise ratio. So the first thing to do is define the filtered signal. This is given by the ensemble average of the correlation function. And what you'll notice is that because the ensemble average of the noise is usually 0 if it's Gaussian and random, this basically means that the filtered signal reduces to this integral here where we have the Fourier transform of the signal times the Fourier transform of my filter function. Now, I can also define a variance in the noise, which is given by this complicated integral over here. But I can use some of the properties of this ensemble average of the noise and its complex conjugate to define a one-sided power spectral density, where the delta here is the Dirac delta function. And then I can basically write my signal to noise ratio in this form here. Now the next thing I want to do is I want to define a noise weighted inner product. For those of you who remember your quantum mechanics courses, imagine instead of signals, I'm dealing with two wave functions. Now, the only way that I can get a real number out of two complex wave functions is an integral of this form here. So I would take one wave function, complex conjugate of the second wave function, and then I would have some weighting kernel here, which is dependent on the physical problem that I'm trying to solve. So this is completely similar to that quantum mechanical problem. So we're defining a similar bracket notation for the noise weighted inner product. We have the two Fourier transform products, and our weighting kernel is actually 1 over the one-sided power spectral density, because I'm now integrating between 0 and infinity, not minus infinity to infinity. Then my signal to noise ratio reduces to this, and again, using the analogy of vectors, if I want perfect correlation between my filter function and the signal in my data, then I require that the two functions are parallel to each other. And this allows me to define an optimal linear filter, which is the Fourier transform of my signal, weighted by the one-sided power spectral density with a phase shift. And I can then plug that in here, and if my waveform template exactly matches the signal, then I can define an optimal signal to noise ratio. Now in practice, what you want to do is you want to use whitened noise or whitened data and whitened filters. So instead of dividing everything here by this 1 over the power spectral density, I would basically divide my signal by the square root of this and my template by the square root of this, and then I'm dealing with whitened data and whitened templates. So the response to a gravitational wave as it comes in on each detector is basically a linear combination between the polarizations of the gravitational wave and the antenna response functions. So depending on the physical problem that you're looking for, the number of parameters can be as low as 9, it can be as high as 17. So let's work out where they actually come from. So I'm going to set up a coordinate system here on the Earth and a coordinate system on the emitting binary, which is sending gravitational waves towards the Earth. And as we go through, you'll see that the parameters either appear in the polarizations or in the antenna response functions, but they never appear in both at the same time. So we can define the parameters as being either extrinsic or intrinsic. We can take the extrinsic parameters as essentially being positional parameters. So the easiest one to define is the distance, and I'm going to give a parameter count over here. Then after that, we have the two sky angles defining the position of the source in the sky. we can define an inclination, an orbital inclination of the binary with respect to the line of sight that we have on Earth. And this is given by this form here if we have a non-spinning binary, and this form here if the binary is spinning. We then define a polarization angle, and this is basically the rotation of the two triads with respect to each other, because we don't expect all of the axes to line up. And then finally, we can define a reference time and a reference phase. You can take this as the time of arrival at the center of the Earth, or you can take it as being the time and phase of coalescence. The choice is arbitrary. Finally, we have the intrinsic parameters, which essentially control the dynamics of the system, and these will appear in the phase of the two polarizations only. So these are the two masses of the binary. There's 6 spin parameters, and if you have a binary neutron star, we also can now try and measure the tidal deformation of the neutron star. So match filtering is very much dependent on having an extremely accurate model of the phase of the signal. Doesn't really matter about the amplitude, but the phase is absolutely crucial. And the problem that we have in general relativity is that there's no solution to the two-body problem. So we need to use a combination of analytical relativity and numerical relativity. So if I look at the time domain morphology of the waveform, I can split it up into 3 different regions. I have the in-spiral down here, which I can describe using post-Newtonian theory. I have the late in-spiral in merger, which requires numerical relativity. And then once the final black hole has formed, it kind of oscillates like a bell that's been struck. And this is the ring down part, and can be described by black hole perturbation theory. So in the in-spiral, we assume that the orbital velocity is much, much less than the speed of light. So these are kind of slow motion orbits. We can write the two polarizations in the time domain as an amplitude times the cosine or sine of a phase. I want to just bring your attention to the fact that the amplitudes of the polarizations are inversely proportional to the luminosity distance. And we define a gravitational wave phase here, which is twice the orbital phase. Then what we can do is we can expand that phase as a post-Newtonian expansion of this form here, usually in terms of a very small parameter, which we're going to take to be this post-Newtonian velocity v. And each of the subscripts here corresponds to the power of v in that correction. So this would have v over c squared, v over c cubed, etc. And because of the fact that we're assuming an adiabatic in spiral, we can use the energy balance equation, which basically tells us that the energy flux of gravitational waves coming out of the system is exactly equal to the rate of change of the orbital energy. So at this point in the in-spiral, the gravitational waves are now the dominant mechanism for the shrinking of the binary. And using that, we can calculate the phase evolution either as a set of coupled differential equations or as a set of coupled integral equations. And the thing I want to draw your attention to is that in every case, we have this ratio here between the derivative of the orbital energy with respect to velocity and the energy flux. And it appears in all these equations here as well. And this is important because both of these functions have got a post-Newtonian or power series solution. And how we treat that ratio can lead to different families of post-Newtonian waveforms. So the easiest thing to do is just to leave everything as the ratio of the two polynomials and carry out your calculations. You could also expand the denominator and multiply through by the numerator and truncate at the sufficient post-Newtonian order, and that'll give you a different family of waveforms. The problem is with post-Newtonian theory is that it's asymptotically divergent. This means that going to a higher order of approximation doesn't always guarantee you a better or more accurate solution. So your solution can actually oscillate very, very kind of wildly. We also kind of know from theory that the post-Newtonian theory should break down as we approach the last stable orbit, but in practice we found that it actually breaks down much sooner than that. So that means that for the late in spiral and for the merger, we need to use numerical relativity. This is a very computationally intensive exercise, and a small number of cycles, so kind of on the order of tens, can take many, many months on a supercomputer. So this is a nice simulation from the SXS group. Down here at the bottom, if you can see, we have the waveform as the two bodies spiral in. And here you can see the deformation of space-time around the two black holes. And it gets more and more intense until we have the the final kind of fusion and ring down. Now, numerical relativity will become even more important as we try and model systems that have matter in them. We cannot find an analytic solution if there's a neutron star or if there's a binary neutron star. We need numerical relativity to model all the matter interactions and how it affects the orbits. We need to do all that numerically. As I said, the ring down is when the final black hole is oscillating back to a steady state and it's emitting gravitational waves. We have an analytic solution and the energy is radiated in a series of quasi-normal modes. To this point, we haven't actually seen the quasi-normal modes, but it's something that we hope to detect with future detectors. So numerical relativity waveforms are much more accurate than the analytical waveforms, but they're also very, very expensive to generate. They're also very expensive to use. We can't use them for data analysis purposes. So because of that, we use three different types of waveforms. We use analytical relativity or post-Newtonian waveforms, but in this case we have the in-spiral part only. We then have hybrid waveforms, which are the effective one-body and the isomorph phenom waveforms. They both solve the dynamics in different ways. One of them evolves the Hamiltonian along the trajectory and solves a set of couple of differential equations. The other one is done directly in the Fourier domain. The kind of important thing is that both are calibrated essentially with each other and with numerical relativity. So they're both very, very accurate. The reason we need many families is that, first of all, we don't know if general relativity is the correct model of gravity. Because we're using approximated waveforms, we don't also know how good our waveforms actually are. So having different families of waveforms allows us to control the waveform systematics and gives us confidence in our analysis. So as we saw yesterday, it's easiest to work in the Fourier domain. And some people it's unclear at times why we should do this in the Fourier domain. So let me take a sine wave at 50 Hertz and some random Gaussian noise, and let me bury my signal in the noise. So down here, you can't actually see the sinusoid in the time domain. However, if I now shift to the Fourier domain, if I took the Fourier transform of the noiseless signal, I would see this delta function at 50 Hertz. You can see if I come down here that by taking the Fourier transform, that my signal now stands up way above the noise. So this is one of the main reasons for working in the Fourier domain. Because of that, we need Fourier domain waveforms. I'm not going to go through all the details here, just to say that we use a stationary phase approximation. And if you follow through this recipe here, you end up with waveforms of this form. So the amplitude has an f to the minus 7/6 behavior in the in-spiral part. So if I look at the morphology of the amplitude in the Fourier domain, I can see that I've got this nice f to the minus 6 behavior right up to merger, and then the power law changes until I get to the ring down frequency, and then it drops off very quickly after that. One of the questions that we constantly get asked when we give these types of presentations is, people have seen this picture before, and it's always kind of strange for people to understand why this very, very short waveform here has a much higher signal-to-noise ratio than these two other much longer waveforms. Before I explain, I should also point out that recently 15, 10, 12 got a promotion. It's no longer an LVT, it's now a GW. So the main reason for why this signal here produced the highest signal-to-noise ratio is that if you look in the Fourier domain, we have a very, very short in-spiral, and then the system merges and goes into ring down right in the most sensitive part of the detector. The other two waveforms, which were lower masses, have much longer in spirals. So we see that we have a very, very long in spiral, and then we get the merger and ring down in part of the frequency band where we're basically dominated by the photon shot noise of the detector. So that's one of the main reasons why we have the disparity in signal-to-noise ratios. So how do we actually sample the data? So if you're doing an exercise, we all know how to do a continuous Fourier transform. But we want to represent everything on the computer, so we actually need to digitize our signal. So instead of this continuous h of t, we're going to have samples at different time steps. So we know the basic prescription. You define a sampling frequency, and then that gives you your sampling interval. Once we've done all that, we can define a discrete Fourier transform, and everything is good. except that we need to know how to choose the sampling frequency, because if you get it wrong, you're going to really mess up. So this is basically given by the Nyquist, or more accurately, the Nyquist-Shannon theorem, which basically says that if I have a signal with a maximum frequency component of f max, and I define that to be my Nyquist or critical frequency, then my sampling frequency has to be equal to or greater than twice the Nyquist frequency. I can then define my sampling interval as 1 over the sampling frequency, and things are good. If I sample at less than twice the Nyquist frequency, then I get aliasing. So this means that if you take a data set, LIGO Virgo data set, and it's sampled at 4096 hertz, it means that the highest frequency component of a signal that I can actually resolve is 2048 hertz. If you want to go for a signal higher than that, you need to use the full 16 kilohertz data set. So why is the sampling frequency so important? Well, the Nyquist theorem basically says that if I have a sinusoid and I sample at twice the Nyquist frequency, I'm getting 2 sample points per cycle, usually at the peak and at the trough. And while this sawtooth kind of waveform doesn't look very, very nice, it actually contains all of the necessary information that I need to represent the signal. So you might ask, what happens if I oversample? So let's go to 4 times the Nyquist frequency. Well, you'll find out that for your actual numerical calculations, nothing changes because you're already encompassing all the information. All you're actually doing is you're increasing the physical size of the waveform that you're storing on your hard drive, right? You're not gaining any extra information. And if you want to produce pictures, then you get something that looks a lot more like a sine wave than the sawtooth kind of triangular waveform. So now what happens if I undersample? Well, I no longer sample at the various peaks and troughs, and sometimes I'm only getting 1 data point per signal. So if I take the Fourier transform of this undersampled data, it basically turns out that it corresponds to a sine wave with a frequency of 2 hertz, right? Not the 10 hertz that I was hoping to sample. And this is dangerous because not only am I losing information, but I'm also changing the information of my data. So that's why you want to avoid that at all costs. We went through this yesterday. We need to define a detection band by basically bandpassing the data. And this was also covered a little bit yesterday about windowing the data. So why is windowing important? So here's my in-spiral waveform. And if I look at the Fourier transform, I basically see that I don't have something that starts at, say, 40 hertz and kind of finishes completely at the last stable orbit. I've got this excess power in the side lobes, and instead of a nice f to the minus 3 evolution of the amplitude, I've got these kind of bumps and oscillations. So what's actually going on? If I just do a naive analysis, then my signal essentially corresponds to something that starts abruptly at t equals 0 and finishes abruptly at the last stable orbit. This is equivalent to taking my waveform and multiplying it by a rectangular window function. So if I take the Fourier transform of just the window function, I see that I have a very, very slow drop-off in the side lobes, and I get a lot of spectral leakage at higher frequencies. So we need to basically treat that. And one of the ways you can do it, and this is a very kind of naive way of doing it, is you can use a half-hand window. And when I say half-hand, I basically mean that I'm applying a half-hand window at the start here, which tapers the beginning, and a half-hand window at the end, which tapers the end. And this is not the optimal way of windowing, but it serves the purpose that it shows that you basically get a much faster drop-off now in the amplitude of the side lobe. So I'm killing my spectral leakage. And if I use a half Blackman window, then at higher frequencies, I get even more truncation. So let's go back to my waveform and apply the half-hand window. So you can see that I'm basically attenuating the signal at the beginning and at the end. But if I look at the Fourier transform, I now have killed most of the oscillations in the main part, and I'm also killing all this excess spectral leakage. So even using a very, very simple and naive windowing function does serve to get rid of a lot of the excess power. So let's tie it all together. And I want to very, 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 very heavily emphasize that this is not how we do the science, right? What I'm going to show you next is for illustrative purposes only. So let's take some data, and this is a nice video put together by Mark Hannam and the guys at Cardiff. So here's my data in blue, and here's a template which I'm going to start off with a distance value of 800 megaparsecs and a total mass of 200 solar masses. And what I want to show you is, again, that match filtering is absolutely critically defined by the phase evolution and the phase modeling of my template. So let's just move the luminosity distance. So basically I'm taking my source and I'm just moving it in and out in the universe. And you can see that basically all I've done is I've shifted the amplitude. I haven't changed the phase in any way, shape or form. Now I'm going to change the total mass, and the total mass appears in the phase of the two polarizations. And you can see that by changing the total mass, I now start to squeeze my waveform enough that I can now get a proper coherent match between my template and the background signal. And then for cleanup, I need to kind of do the rotation angles, change the position in the skies, change the inclination, and that gives you that final piece of the puzzle. So once again, this is not how we actually do the science. How we actually do the science, Ian and Vivian will describe after me. So let's move on to the actual science that we do. So let's look at the two advanced detector runs. So the first one was in late 2015, and the second one started in late 2016 and ran until the end of August 2017. All in all, we've discovered 10 binary black holes. And one of the things that I want to draw your attention to is the massive energy output from these mergers. They are vastly outshining everything else in the universe in terms of gravitational waves. And you know, in some cases, we have up to 5 solar masses being converted into gravitational waves. That is a phenomenal amount of energy. We've also detected our most massive and distant source so far. So individual masses of 50 and 34 solar masses. It left behind a black hole of 80 solar masses. And this is out at a distance of about 2.7 gigaparsecs, or a redshift of almost a half. So we're really starting to probe cosmological distances. If you go to this website here, there's this nice movie which shows numerical relativity simulations of the different binary black holes that we've detected so far, and it gives you a nice representation of the relative difference in size between the respective black holes. So if we look at the masses, you can see that we've basically got a large spread in masses, and we've produced quite a zoo of final black holes. So everything from about 20 to about 80 solar masses. In terms of the distance, again, we basically are starting to push out into the universe. So we're getting out to a redshift of about 0.5. And one of the things that we'd also like to measure is the spin component of the waveforms. The problem with spins is that spins are a subdominant effect in the actual waveform model. They're also highly correlated with the individual mass parameters, so it's actually very, very difficult to extract information at present on the spins. The one thing I'll say is that at the moment we have absolutely no evidence of precession in any of the systems that we've seen. We've also found the first ever binary neutron star and our best result event at 16 square degrees. So Alan covered this yesterday, but another common question that we get is, well, how do you know it was a binary neutron star? And the easiest way to know that it's a binary neutron star is to look at the duration of the signal in the detector from a given reference frequency. So you can see that all the black holes have merged within a second, maybe a second and a half. The binary neutron star is lasting, in this graphic here, about maybe 50, 60 seconds. The only way you can have a waveform that long, starting at the same reference frequency as all the others, is to basically make the masses as small as possible. So we get into the range of binary neutron stars. We would kind of know if we had, say, a black hole neutron star system, because then we would have waveforms that would be lasting on the order of maybe 15 to 20 seconds if you start at a reference frequency of about maybe 30 hertz. So we can kind of get a quick glimpse into what these systems actually are just by looking at the time in the detector. And then this has all opened up the field of gravitational wave astronomy. And in fact, not just astronomy, but we can also do stuff on fundamental physics, extreme matter, cosmology, well, cosmology twice even. So let's first of all look at fundamental physics. So we know from the binary neutron star that there was a gamma ray emission about 2 seconds after the merger of the binary neutron star. This allows us to put a constraint on the speed of gravitational waves. And it's actually about 1.75 seconds. So this allows us to put this phenomenally tight constraint on the difference between the speed of gravitational waves and the speed of photons. Now, we have a very, very strong theory group here at APC. A lot of them working on things like beyond Horndeski theories for many, many years. And in 2 seconds, all of their work was completely gone, right? So once we discovered the binary neutron star, all of these alternative theories of gravity are all completely ruled out. On top of that, so are all of these other theories here. So one of the other things we can look at is calculating the Shapira delay. So here is my PPN parameter. And what's important here is this is the potential that models the dark matter distribution between the observer and the emitting source of gravitational waves. And as a first approximation, you can basically take the dark matter distribution of the halo of the Milky Way and the dark matter distribution of the halo of the emitting galaxy and kind of ignore everything in between. And if you do that, you basically get this constraint here on the difference between the PPN parameter for gravitational waves and for electromagnetic theory. About 6 weeks after we published our result, there was another group who basically used a much more sophisticated model of the dark matter distribution, and they basically tightened the constraint to this value here. This then killed, essentially, all Mond-like theories. Because with these values, if you do have a Mond-like theory, then you'd expect a difference of about 1,000 days between the arrival time of the gamma rays and the arrival time of the gravitational waves. And because we saw them within 2 seconds of each other, there's no way that these Mond-like theories can be correct. So one of the other things we can do is we can essentially test general relativity, or to start off with, we can test post-Newtonian theory. So here's my post-Newtonian phase in the Fourier domain. And we also know that if there are alternative theories of gravity, that their dominant effect should occur at different post-Newtonian orders. So we have Einstein ether theory at f to the minus 5/3, massive graviton at f to the minus 1, dynamical Chern-Simons at f to the minus 1/3. And it's not in here, but if you then put an f to the minus 7/3 or a minus 1 post-Newtonian order term, you can try and model dipole radiation. And then what you can do is you can basically test to see, are there non-GR extensions to my general relativity phase? And it's been shown that just finding the dominant effect is enough, right? So if I go back here, while the dominant effect of, say, Einstein ether would be at this post-Newtonian value, it would also change all these other coefficients. But to basically see if general relativity is correct or not, I just need to check if that dominant effect exists. I don't need to check all the higher coefficients. And what do we get? So with the very, very first detection, these are the constraints that are placed by the most relativistic binary pulsar that we know of. And these are the constraints on the post-Newtonian coefficients in the inspiral from 1509-14. Now, the one thing that I would like to highlight here is that this pulsar bound comes from 10 years of observation. The gravitational wave bound comes from 200 milliseconds of observation. So you can see that we do very, very well with an extremely short signal. And this is where we are now. So change of color, the orange squares here correspond to the blue circles here. and what you want to focus on are the diamonds at the bottom. So you can see in every case with the 11 binary black holes that we found, or sorry, the 10 binary black holes that we found, and remembering that not every one of them will contribute equally to the analysis, you can see that in most cases we've basically reduced the potential deformation of the post-Newtonian coefficients by an order of magnitude. And then we can do that for the entire waveform. We can look at the merger and ring down as well. So again, this was our initial detection, and here's what we have now with the 10 black holes. If general relativity is correct, the value should be 0, and you can see that now all of our posterior distributions encompass 0, and some of them are actually extremely tight around 0. One of the other things we can do is we can test to see, is there a massive graviton? If there's a massive graviton, it'll basically change, it'll induce a dispersion relationship into the movement of the gravitational waves, and it'll modify the group velocity to this form here. In general relativity, this value A here would be exactly 0. And it very, very kind of simply changes the phase of our gravitational wave. So we can again use match filtering to see if there's this deviation. The different values of A's and alphas, they correspond to different alternative theories of gravity, so we can do multiple tests. And basically what we find is this. The first thing I want to bring your attention to are the units here on the left-hand side. We're already working in pico-electron volts. And you can see that the constraints on all of these parameters are on the order of 10 to the minus 20 to 10 to the minus 19 pico-electron volts. So we're seeing virtually no deviations from general relativity whatsoever. This allows us, if you remember that A naught here corresponds to the massive graviton, the current results that we have allow us to put this bound on the mass of the graviton or the Compton wavelength of the graviton. And this is about 2.5 times better than what we had with the initial detections. One of the other things, and this was a question yesterday, was can we check for other polarizations of the gravitational waves? In generic metric theories, you can have up to 6 polarizations. So with the inclusion of advanced Virgo, it allows us to break some of the degeneracies and try and test for some of the polarizations. There was a nice study which showed that it doesn't matter what the form of the polarization of the gravitational wave polarizations are, so the H plus and H cross. What matters is the geometric projection of the signal onto the detectors. So all you have to do is test the antenna response functions for the different alternative modes. And what we found was that if you basically assume that nature is either purely tensorial, purely vectorial, or purely scalar, that tensor is preferred over vector with a base factor of 200 to 1, and tensor is preferred over scalar with a base factor of 1,000 to 1. So the question that you should ask yourself, and again, you know, we do a very, very rigorous, very complicated analysis, but sometimes just looking at stuff, you know, gives you an off-the-bat answer. The question is, should we be really surprised by this result, right? So if I look again at the first detection, I think this is the Livingston detector, and I think this is where the signal-to-noise ratio was highest. It's very, very difficult to see here, but there's a light blue squiggle in the background, which is the data. The darker line is the family of best fit waveforms, which assume from the very, very beginning that general relativity is correct, and there's only 2 tensor modes. And we can see that the phase coherence between the template and the background data is very, very good. It's accurate at the level of 96%. That means that if there is a non-tensorial component in the waveform, that we can already say that it must be at the 4% or less level. So let's move on to what we can do for astrophysics. Astrophysics is difficult, right? We, hand on heart, know virtually nothing about the evolution of binary systems. There's too many unknowns, there's too many kind of handles and knobs that can still be turned. We don't know if the systems that we found are standard galactic field binaries, so you start off with 2 stars, they go through binary evolution, there's a couple of supernova, and we end up with a compact binary system. or if they're dynamical capture systems. So you have an isolated star in a globular cluster, it goes through a single star evolution, it goes supernova, it leaves behind a remnant, and then that remnant gets captured by some other compact object to form a binary. At the moment, we can't say. Even if we could, things are still very, very difficult because we still don't know how the common envelope phase actually works. This is when the larger star envelops the smaller star or even a compact object. We don't know how that physically works yet. We don't know the role of metallicity. The one thing that we can say is that the systems that we've seen seem to point to formation in parts of the universe where the metallicity is quite low. It's the only way that we can get black holes as big as the ones we've seen. We still don't understand the role of natal kicks in supernovae. We don't understand how many of these initial systems stay bound after the first or even the second supernovae. We don't know how mass transfer changes the evolution of the binary. This is something that we're still working on to try and understand. And you can ask yourself, what is the merger rate for all these systems? One of the things that we're hoping to try and investigate in the next few years is astrophysics predicts the possibility of two mass gaps in the distribution of compact objects. So we have one mass gap down here where we have a gap between 3 and about 5 solar masses, and we have another gap up here from approximately 50 solar masses onwards. So this bound here at 3 solar masses is given by nuclear equation of state. It basically predicts the largest possible compact neutron star that you can form. And from equations of state, you get a limit of about 3 solar masses. The 5 solar mass limit comes from stellar astrophysics, and it basically predicts, first of all, the smallest star that can produce a black hole, and then the smallest black hole that star can form, and that should be theoretically greater than 5 solar masses. There's another gap up here at 50 solar masses, which is from pair instability supernovae. So these are kind of runaway supernovae where everything happens so violently that essentially the star blows itself apart and doesn't leave a black hole behind. One of the things that we have been able to do is set limits on the rates of the system. So for O3, we predict somewhere at the end of O2, we predicted somewhere in the region of 10 to 100 binary black holes per cubic gigaparsec per year, and somewhere between 110 and 4,000 binary neutron stars per gigaparsec per year. This is already much tighter than the constraints we had from the initial detections, and we hope to go kind of better in the next few years. I'm going to very, very quickly go through this. Now that we can detect neutron stars and binary neutron star mergers, we should be able to say something about extreme matter in the equation of state. Nuclear physics tries to put a bound on this mass radius plot, and these are all the different families of potential equation of state models. We know from observation that pulsars have different distributions, whether they're recycled, whether they're slow, or if they're appearing in a binary system. In that case, we expect the mass to peak at about 1.3 solar masses. From observation as well, we also know that the most massive neutron star that we've seen is roughly 2 solar masses. So if you put that first bound in on the mass radius plot, it basically rules out all of these gray curves here. Any curve that doesn't poke its head above the dotted line is automatically ruled out through EM observation. When we first did the analysis of the binary neutron star, we were able to put a bound on the tidal deformation of a 1.4 solar mass binary to something less than 900. This was analysis starting at 30 Hertz and ending at 2048 Hertz. We then did a better analysis where we started 7 Hertz lower. Doesn't sound very much, but 7 Hertz lower gets us approximately 1,500 extra gravitational wave cycles. We then have no assumptions on the binary. We also use the fact that now we have an EM counterpart to localize the system in the sky. And the bound on the tidal deformability became 20% smaller. And then we did an even better analysis where we assumed that both neutron stars had identical equations of state. We folded in the information from observation, etc. And the final result that we have at the moment is that the tidal deformation of a 1.4 solar mass neutron star is 190 plus these errors. So down from the original something less than or equal to 900. We also can make a statement now on the state of nuclear matter. So we were able to calculate the pressure at twice nuclear density. And this allows us to put some constraints on where the GW170817 binary might actually lie in this mass radius plot. So if you use gravitational wave information only, it fits into this green box. If you fold in the observational evidence, then it shrinks in radius to this green box here. So it doesn't rule out that many of the theories, right? So it's a result, but it's not a fantastic result, but it shows that we're kind of making a contribution. I'll very quickly go through this. People ask what the merger or what the remnant is. The short answer is from gravitational waves, we don't know. And from electromagnetic theory, they probably don't know either. But the thing that everybody is sure about is that they can now explain how all the higher elements in the periodic table exist through neutron star mergers. And my last slides are, we also want to try and do cosmology. You can do it two ways. You can use distance ladders from astrophysics, or you can use CMB kind of information from cosmology. This is what we get from gravitational waves. And again, it's not a fantastic result, but it is based on one event. And more importantly, we don't need cosmic distance ladders. We measure the luminosity distance to the source directly. So as long as we have that measurement and we have an electromagnetic counterpart, we get a few tens of binary neutron stars. We can really shrink this posterior down to something that's actually useful. And that's my last slide. Thank you very much.